record. Nice try. All right. So just a little bit of review. What did we say last day? We talked about different sampling techniques. We talked about bias and random sampling and sampling distributions. So we talked about data versus sampling distributions. And we're going to keep talking about that today. We talked about random sampling and bias. I'll say and bias, although the reason we do random sampling is to try to eliminate bias or at least minimize the bias, which led us to, okay, well, what are some random sampling techniques? So things like stratified random sampling, cluster sampling, multi-stage sampling, blah, blah, blah. Not super important for our purposes, but it's good to have a handle on that stuff. So then random sampling techniques, or methods, I should say. Also talked about regression to the mean. That's just kind of a fun thing, so I won't include that on here, right? But where extreme values over time tend towards just the average, the mean. Okay, not much in terms of review, but that's it. So what we didn't get to quite was, okay, the data distribution versus the sampling distributions. Well, the data, we're referring to the raw data, right? But really what we're talking about is in most of our statistics that we've seen already, so hypothesis testing, confidence intervals, those are about statistics, right? Sample statistics. So X bar or the sample proportion, right? And so all these things that we want to learn about rely on knowing the sampling distribution. Okay? So how can I summarize all of that? Okay, here we go. I'm going to say in most statistical analyses, we want to learn about, or we want to use a statistic to learn about the population parameter, right? So we want to use a sample statistic, although if I say statistic, it's implied that it's from the sample because that's the definition, right? But I just want to emphasize here the sample statistic to learn about, and again, I'm just going to be redundant, but also to emphasize the population parameter. For example, right, we use X bar, which is the sample mean, to learn about mu. Right. So X bar is what we use in our test statistic to find the p-value, right? And so T equals X bar minus mu over S over root N, for example, right? So we use this to find, we use X bar to learn about mu, the hypothesized mu, to find the p-value, to draw a conclusion about the hypothesis, draw a conclusion about H naught might be something like mu equals mu naught in this case, so this should be mu naught. And HA is maybe mu is not equal to mu naught, or less than or greater than, depending on the scenario, right? The default is not equal to, we usually just use not equal to. Especially in data science, we don't really care. Yeah. So when we use X bar to learn about mu, what we're doing when we use the t distribution, for example, is we assume that it follows the t distribution, right? So in doing this calculation here, this assumes X bar follows a t distribution. X bar follows a t distribution. Which it does, right? It does. Which it does, right? With n minus 1 degrees of freedom. But it kind of puts X bar into this box. Okay, so a sample mean always has to follow a normal distribution, right? And so we said X bar follows this normal distribution with a mean mu and a standard deviation sigma over root n. And then we try to make that work, but that's really, really old school stuff. And we still use it. And if you're, if you're publishing papers or if you're reading published papers, they're still going to use traditional statistics. So it's important that you know what it is, right? But in terms of what we are going to be doing is we're going to move away from saying, okay, well, X bar must follow this t distribution. And we're going to say, well, what if I just create a distribution for X bar? And then I can just use that distribution to figure out the probabilities that I need, right? And so that's where the bootstrap comes in. So here, when we're relying on these set distributions, that's very traditional and pretty old school stuff. Okay. And so we had to rely on these predetermined or prescribed, let's call them prescribed. So we had to rely on prescribed sampling distributions, such as X bar follows a normal distribution with a mean mu and a standard deviation sigma over root n to figure out the shape of X bar. Okay. For as long as we didn't have computing power. So it wasn't really until the textbook says the 80s, but then it wasn't even widely available in the 80s, right? This computing power. And so I would say probably later than the 80s. Of course, statistics has been around for a very, very long time, hundreds and hundreds of years. They had to do stuff without computers. So that's where traditional statistics comes from. But we had to rely on prescribed sampling distributions such as this. Okay. Before computers slash computing power. There was that brief moment in time where, sure, we had computers, but no real computing power. But right, so now we have all this computer power. Our phones are incredible, right? And we can run all these simulations, and it doesn't bother us. But we're basically going back to what they did to establish these prescribed sampling distributions. So how did they arrive that X bar typically follows a normal distribution centered on the mean with a standard deviation of sigma over root n? Well, they looked at many samples of X bar and figured out, okay, this tends to fit most of the time, right? Assuming it follows these criteria, right? So we're basically gonna recreate the wheel, but it's gonna be more flexible, okay? And so, this is the base of traditional statistics. So now what we're going to do is, with kind of our computers, any computer will do it. It's very easy and not that hard. Although the doing it is hard. Obviously, you have to code it in R and you have to tell it what to do. That part's hard. I'll give you that much. But in terms of what the computer is doing, the algorithm is not hard. Okay? And so the modern approach to inference, remember, inference is the umbrella term that we use for hypothesis testing and confidence intervals. Hypothesis testing and confidence intervals. So the modern approach to inference is to use the bootstrap. Okay. Should clean that up. Doesn't say bootstrap, does it? Bootstrap. Okay. Which is kind of cute if you think about it. You have to pull yourself up by the bootstraps. It's like, give your head a shake. Okay, so this is what we're going to use as data scientists more than the traditional statistical techniques. Okay. For most applications or for most analyses, right, the bootstrap is going to get us what we need without having to rely on, okay, does it follow a normal distribution? Does it follow a binomial distribution? Does it follow a Poisson? That kind of thing. That'll be helpful, right? To kind of, those words, they mean something, right? But for most applications, we're going to be able to just take the sample and regenerate it and produce our own sampling distribution. So for most applications, or I'll say analyses, in data science, the bootstrap will suffice. So what is the bootstrap? Conveniently, I've got a fresh page here. So the bootstrap, just like all the time, everything that we do relies on having a good sample. So a randomly selected sample, it's representative of the population. So again, that's not different. We still need that, right? So that's why we had to talk about these different sampling techniques. Although I kind of rushed through it, I'm like, oh yeah, get someone else to do it. Just don't do it yourself. Right, and so the bootstrap relies on having a good sample. A good sample, which means it's representative of the population, representative of the population. Okay. There's no way to check that though. How do I know if my sample is representative? There's no way that I could know that, right? But I have to assume, so that's when you have to go back and you have to look, okay, well, how was the sample collected? And then you have to be satisfied with how it was collected. Is it random? Then you can assume that it's a good sample, but there's really no way to check that. Okay. So the bootstrap relies on having a good sample. And I guess I put a period here, but I'll keep going with this run-on sentence. And allows us to estimate the sampling distribution. The sampling distribution of any statistic, or of any, I'll say sample statistic. It's redundant, but. So how does the bootstrap work? Oh boy. So I've got one sample, that's all I need, right? I've collected a random sample of sales from a store, let's say, right? And so I have a sample, and now I want to know, okay, what's the probability that, I don't know, I sell more than $500 on average, something like that. I don't know. So as soon as I want to find probabilities, okay, what do I need to do? Well, then I need this sampling distribution. So, okay, I have one sample. That's just the distribution of the data. I can make a histogram of that and I can look at that. But what I want is the distribution of the mean. So this sample gives me one mean. So what I need to do is I'm going to use my sample as if it's the population. And what I'm going to do is I'm going to randomly sample with replacement from my sample. So then I can generate this fake data from my original sample. So you can see how it's important that that original sample is good, right? Because then what I can do is I take a random sample of size 50, let's say, for example, and then I can have a list of numbers. They were randomly selected from my sample. I can calculate the mean, and then I can do that again, take another 50, I can calculate the mean, and then I take another random sample of size 50, I can calculate the mean. So slowly I'm accumulating these means, right? And so then I'll have a data set of the means that I've generated. Then that, if I make a histogram of those means, that gives me the sampling distribution of the mean. It'll end up looking approximately normal just because that's how the mean behaves, right? But what we can do is we can use that distribution that we've just generated, and it doesn't rely on things, you know, coming from a relatively normal distribution or anything like that. We're just taking information that we already have, and then we're regenerating it many, many times over, which feels a little witchcrafty, right? Especially in the beginning, but it works, right? Especially because we're doing it with replacement. So let's go through those steps. Step one, you're going to draw a value. So select a value, I'll say draw a value. You know what? I'll say randomly select. Let's be proper about it. Randomly select a value from the original sample. So you only have one original sample, and that's all you need. Original sample. And I'm going to call this OS, original sample, just because we need to be able to refer to them. And so you randomly select a value from the original sample and you record it to create the start of a new sample. To create the start of a new sample, which I'll call NS, new sample. Okay. Once you've recorded it, you put it back into the bin. Okay, so then you're going to replace the value into the original sample OS. So we're drawing with replacement. Do you guys have to take a probability course? No, I don't think so. I'd have to teach it, and I hate probability. Drawing with replacement might sound familiar though, maybe. I know, gross. Which means that in theory, I could randomly select that exact same value again, but that's okay. Right? The probability is low, so it's fine. And that's how random selection works. So then what you're going to do is you're going to repeat this n times. So repeat step 1 n times. Right? So this means that you have created a sample of size n. This creates a sample of size n. Yeah. So then what we're going to do is we're going to calculate the sample statistics, such as the mean or the proportion, whatever it is that we're interested in. Okay. Record the sample statistic of interest record the sample statistic of interest for example, the sample mean x bar. Okay. So now you have one sample which generates one sample mean. Now you have to repeat that process many, many times, right? In order to build up this distribution of means. So now, step 4, you're going to repeat 1 through 3 capital R times. Ugh. It's all about the context, right? R is the programming language, but not in this case. It's also the correlation, but not in this case, right? So here it's just to denote R times. I think I decided to stick with this notation from the textbook because the function in R also uses a capital R. I know, crazy. R stands for repetitions. In this case. So now what we're really interested in is this sample of R sample statistics, right? So now we're going to have R X bars, for example. This results in a sample of R sample statistics. Right, for example, R, or sorry, I'll say a sample of R X bars. Can you imagine if some poor soul stumbled upon these notes? It doesn't make sense. A sample of R X bars. Had to be there. You had to be there. Okay. Okay. Now I have my sample of X bars, which is what I wanted. I can probably let go of those bootstraps. They're all, that's fine. What we got, what we needed, right? Which was a sample of X bars. And so now I can use this distribution of those statistics in order to answer questions like, is the mean different from some number? Well, I just look at it. Is that within the realm of this distribution? Yes or no? I can make confidence intervals, right, by just using the sampling distribution. So step 5, using the sample of statistics. This is when I stopped saying sample statistics. It had to stop at some point, right? It's redundant. I'll do that. Statistics means it's from the sample. So using the sample of statistics, which I'm referring to, for example, the sample of R means. We can look at the distribution. We can look at the distribution. Right, using a histogram, for example, or even just the raw values is fine too. Using a histogram or whatever you prefer. This is the sampling distribution. So once I have this collection of means and I have R means now, then what I can do is I can calculate things like, I can find the mean of the means, right? Great. I can find the standard deviation of the means, which in the past we've called the standard error, right? The standard error is something like S over root n, because it has to be for the X bars. But now the standard deviation of the X bars is the standard error. Oh boy. Oh boy, here we go. We can use the sampling distribution the sampling distribution to calculate the standard deviation which in the past we've called the standard error. Standard error of the estimate. All right. So if we go back to kind of our traditional version here, the sigma over root n, that's the standard error of the estimate X bar. So here, this is the standard error of X bar, which we estimate by S over root n. But we don't need to do that anymore because now I have a sample of X bars and I don't need to keep guessing what it might look like. I can just generate these samples of X bars using the bootstrap, and then I can look at it and I can use those values. I can calculate the standard deviation of those values. And then that is my estimate for the standard error. Very confusing in the beginning and maybe halfway through too. Have you guys used the bootstrap in other courses yet? Or no? Well, I assumed you hadn't. Don't worry. I wasn't thinking that you had. Do you guys have Claude for anything yet? Claude, does he teach any of your courses yet? Yeah. And are you taking that yet? Okay. Oh, I guess it depends on how you're going through it. Okay. So he might talk about the bootstrap, but probably not because he'll stick to kind of traditional stuff. Okay. So the sampling distribution, let's just talk about, okay, so what are the main values of X bar, right? What are the most common values? And also with what variability could we expect in this from this sample? So what I'm going to say is that we usually don't just report a raw value, so an X bar. Well, usually we report it with some buffers. So for the variability, so most commonly we use a confidence interval, right? We say X bar is this, plus or minus a little bit on either side, and then we're 95% confident that we've captured the population mean, right? We don't know what it is, but with these bounds on here, we're 95% confident, for example. And so we'll be able to do that with the bootstrap as well, but I want to kind of link the two. It looks crowded, but it is a page break, so I promise it'll look better once they're separated. So we usually do not report a single statistic on its own, right? We want to include the variability. So we usually do not report a single statistic on its own. We need to include the variability. We need to include the variability. Yeah. So kind of going back to what we do traditionally and what we've seen in the past is if I have to make a confidence interval around X bar, then I can use the t distribution. And so we do this by using confidence intervals. By using / reporting, I should say, reporting confidence intervals. So traditionally, we rely on approximating the sampling distribution and using formulas. So traditionally, we rely on approximating the sampling distribution I'll say sampling. That was sample turned into sampling. The sampling distribution. Traditionally, we rely on approximating the sampling distribution and using formulas such as if I have a sample mean, then I can take that sample mean, that's my best guess. But then what we did in Stat 230, for example, was we said, okay, I'm gonna need a critical value, which in this case has to be a t with n minus 1 degrees of freedom. So usually, I never did that in 230, I think, but we had to say somewhere what the degrees of freedom were. So usually we just jot it down as a subscript times s over root n, which is the estimate of the sample of the standard error of x bar, right? S over root n. But it relies on the t distribution, and then we had to use the t table, and that's what we're moving away from. We don't need to do that anymore. Okay. And so, but this is a way that we could find a confidence interval, and that's the way that we've seen so far, and that's totally valid, totally fine, just not as flexible as the bootstrap. Okay, and so using the bootstrap, how can we do something similar? Well, using the bootstrap, we can find confidence intervals. I guess I should define it here. CI equals confidence interval. It's been a while, so. So using the bootstrap, we can find confidence intervals for any estimate or any statistic that we're interested in. As long as we're able to bootstrap our way to a sample of that statistic, then we can find a confidence interval. Okay, so that means that we don't need to know all these formulas that we worked on, right, in Stat 230. We should know that they're available to us and they exist and people use them, especially in academia. But in terms of kind of getting information to the people, we don't really need that anymore. So using the bootstrap, we can find confidence intervals for any estimate or statistic. Right, X bar, P hat, whatever you want. How? Well, if I have this distribution of X bars, for example, I want to find a confidence interval for X bar, then if I want to find a 95% confidence interval, what I'm going to do is I'm just going to trim off the top and bottom 2.5% of those values. I'm just going to trim them away. And then what I'm left with is my confidence interval, somewhere between here and here, right? 90% confidence interval, 5%, 5%, cut it off, done, right? So kind of fun that you don't need formulas. I feel lost without formulas, but it is a cool way of doing things. So picking up at step 5, right? So now I have this distribution of X bars already. So picking up at step 5 from above, we can calculate an X% confidence interval by doing what? By trimming I'll use the notation and I'll explain what I mean. By trimming 100 minus X% divided by 2% of the R results. Oh, and I should give myself a little bit of space so I can explain what I mean by this notation. I'm bringing it in because they show it in the textbook and they just assume that you're going to know what that means. So I just want to explain. Of the R results from either end of the distribution. And then the trim points are going to be the end points of a bootstrapped confidence interval. Oh boy. The trim points are the end points, right? Lower bound, upper bound of an X% bootstrap confidence interval. So here, it makes more sense if we let X be 90, then if I want to make a 90% confidence interval, then what it's saying is I'm going to trim off 100 minus 90, which is how I got the 10, but then divide it by 2% of the R results from either end, right? So here this says trim 5%, right? Which is 100 minus 90 divided by 2 is 5, right? Trim 5% off each end of the distribution. So if I'm talking about X bar, it will end up, oh, that was a terrible normal distribution. It's going to look something like this. Of course, it's not going to be smooth anymore because we've just got this raw distribution of X bars. But in terms of visualizing, I still find that smoothing it out is, well, a lot quicker, because otherwise I'd have to make all these jaggedy bars, and that's going to take a long time, right? So just imagine here, in theory, So then here I have my distribution of X bars, and it goes to some endpoints here, right? I have some minimum and some maximum because I have R X bars, so I have a finite number of X bars. It's no longer theoretical, right? And so now what I can do is I can trim off, here's 5% of the values and 5% of the values. And then here, this is my 90% confidence interval. I only use 90 because it makes 5 and 5 instead of 2.5, 2.5. But our default is 95%, right? That doesn't matter. Okay. Great. So like I said, the bootstrap is going to be kind of our new weapon of choice, right? We don't need these formulas anymore, but that said, we're just going to review some of these distributions just so we kind of remember what they were. Any questions about the bootstrap though? Just processing. Take a moment, think about it. Guess I should check the chat too. Usually I can't see the chat. Oh, there are 2 in the chat. Oh, thanks, Stormprate. I can't see the chat, but there we go. In machine learning, I guess they talk about the bootstrap, which makes sense. Of course, machine learning would use something so cool. All right, so cool. Make sure that I can skip this page. I can. All right. So this is where I said, if you've got other places to be, you stayed for the mandatory part of class. I understand you guys are swamped because now all I want to do is just review some key parts about the normal distribution, long tail distributions, t-distributions, and I think just the binomial distribution, which is all review, which might be nice. Take a break. All right. So let's review some of those most common distributions that we have relied upon. So let's review some of the more common distributions. Start with the normal distribution. Seems like a pretty good place to start. The normal distribution is the most common sampling distribution, not because it's necessarily true. Very few things actually follow a normal distribution, but it was a good kind of jack of all trades for a really long time. So once they had that one under control, they just kind of made sure, okay, can I use the normal distribution? Okay, good, because I know how that works. I know how to find probabilities using the normal distribution. And so it was a good kind of solution. The most common sampling distribution, oops, is the normal distribution. Pardon? Yeah, the Poisson. It's like, okay, is that the one with the counts in an interval or the intervals between the counts? There's like so many of those. And I can never get Poisson counts, that's fine. But then there's one where you model the time between the counts. And that's then, I want to say, is that the geometry? Anyway, it doesn't matter. Just erase your brains. There's so many. And it's helpful to know those. But with the bootstrap, you can just recreate your sample many times over and then see what happens, right? Then you can find those probabilities. Because how would you find, sorry, to go back to probabilities from the bootstrap, which we didn't really talk about, right? If I want to know the 5%, what's the lowest 5%? Well, that's this cutoff here, right? And so same thing, 50%. So the areas underneath the curve, which are really bars in this case, right? We can figure out, all right, how many of these X bars were less than 30, right? I can go in, I have a list of X bars, I can just count the proportion of them that were less than 30, and then that's the probability, right? And so I can just use that raw information, which is kind of weird. But the most common sampling distribution is the normal distribution, with a side note that very few things are actually truly normally distributed. It's very difficult to get there, but it's a good approximation. So note, very few things are truly normally distributed. Yeah. But we can use the normal distribution and all these traits that we know, things like the 68, 95, 99.7 rule. That's a good rule of thumb, right, for figuring out probabilities, which are areas under the curve, right? And so knowing these things, just like kind of the way back in the day, right? Oh, good. Okay, I have a normal distribution. There are some key things that I know about the normal distribution that I'm going to apply here. So knowing we have a normal distribution, or sorry, a normal sampling distribution, I should say, allows us to approximate probabilities we'll never use something silly like a Z table again, right? We'll use R if we have to, but usually as long as we're able to kind of give rough approximations for these probabilities, that's good enough. Probabilities. Using the empirical rule. Which remember is the 68, 95, 99.7 rule. Oops, 99.7% rule. Can't remember if I told you guys in Stat 230, one time I taught it up at UBCO, and my old supervisor, he was like, oh, you know what? Don't use those silly tables. Just don't do it. It's crazy. And I said, okay, I'm listening, because I hate the tables. I hate the Z tables, T tables, whatever. I think they're stupid and useless because we have software now. And he was like, no, just don't use those tables anymore. How about you try teaching it just using the 68, 95, 99.7 rule? And you can, right? You don't need to know that it's 67.99, right? It's just less than 68, right? That's good enough. right? So you can use these cutoffs and do kind of quick approximations. We don't need to know exact values, right? Is it less than 68? Is it less than 95? Is it less than 99.7, right? Or I guess more than, but I'm thinking about the tails, right? Those p-values. So something like the 68, 95, 99.7 rule might look something like this. I've got mu, and then I've got mu minus sigma, and then mu minus 2 sigma, and mu minus 3 sigma. Same thing, mu plus sigma, mu plus 2 sigma, and mu plus 3 sigma. Right. You can review those if you want to, but they're not going to be important. What I'm trying to say is that, okay, if I know these cutoffs here, and if a value is beyond the green bars, for example, so 2 standard deviations away, then I often reject the null hypothesis, right? And if it's more than 3 standard deviations away, I very likely reject the null hypothesis, because the probability of kind of happening out in these tails just by random chance alone is very, very small, right? So you can use just the 68, 95, 99.7 rule. Thinking back though, do you think that would be more confusing or less confusing than the Z tables? Once you kind of understand how the Z tables work, they're a nice, like, okay, then I go in here and I go find this, and then I have this value, a real value, not just kind of a whimsical approximation. And that's what I found with that group too. I found that they were a little bit like, in the beginning at least, they're like, I want to know a real value. I don't know. It's just a different way to teach it. I tried it. It worked, but went back to this. Mostly because the college is still using tables. So it got weird. Anyways. So in order to use this, right, the empirical rule, or the 68, 95, 99.7 rule, I'll just call it the empirical rule now. I think we're kind of grown up a little bit, right? So to use this, right, to approximate probabilities, then I need to know how many standard deviations I am away from the mean, right? And so to use the empirical rule, we need to know how many standard deviations or sigma, but usually we can kind of replace that with S and get by just fine. An observation, which we usually denote by X bar, is from the mean. Yeah, which that calculation is the Z calculation, right? The Z score, which says X minus mu over sigma. When we calculate Z like this, right, when we figure out how many standard deviations I am away from the mean, we call that standardizing or normalizing X. Standardizing X or normalizing X. I don't tend to use the term normalizing just because it makes it sound like you're turning it into a normal distribution when in fact it has to come from a normal distribution to become a smaller normal distribution centered on 0, standard deviation of 1, right? You're just shrinking it down. So I prefer the term standardizing, but normalizing is a thing as well. So, right, a lot of it hinges on having a normal distribution, of course. So what are some of the ways that we can check that? We can check if we have a normal distribution by using a QQ plot, usually. I can't remember what the hypothesis test is called, but there's also hypothesis tests that you can run to assess normality. Yeah, not worth looking up, but it exists. I'm not going to make you do it though. Cannot remember what it's called. But we can visually assess a normal distribution by using a QQ plot. I think it's quantile plot, but I am not going to write that down because I'm only 99% sure. QQ plot, it looks like this. We've seen them before, but only briefly. I have the Z scores from the data, right? Each data point, I can subtract the mean and divide by the standard deviation, and then I can standardize all those data points. And then here, I guess I'll need a little bit more space down here, but these are the theoretical values. The theoretical values are a normal distribution. So you have the mean and you have the standard deviation of your data. So then we say, okay, then if I have a normal distribution centered on there and with that exact same standard deviation, then I can plot my points and see how far off they are from that theoretical distribution. Put it on the next page here, theoretical values. Are from a perfect normal distribution with the exact same mean and standard deviation as our data. With the exact same mean and standard deviation as our data. So it's really just checking, okay, what if I take that information, I create a perfectly normal distribution, and then I plot it against my raw Z scores, right? Then if X equals Y, right, if they're the same, then I get this diagonal line, right? X equals Y, looks like that, right? And so here, trying to see if I have enough room to write what I need to write here. I'm going to try observed values that fall on this line are the same as the theoretical values. Are the same as the theoretical values. Which means they follow a normal distribution. We do allow some deviation in the tails because the tails are unpredictable, right? And so we do allow a little bit of action here in the tails, but for the most part, if we have a normal distribution, then all those points should be on this straight diagonal line. Okay. Maybe I'll say that here. We allow some deviation in the tails, but in order to be considered normal, right, the majority, most of the points should fall on this straight diagonal line. But in order to be considered normal, most of the points should fall on the straight diagonal line. On this straight diagonal line. I think that's probably good for today. We do go, yeah, that's good for today. We'll keep talking about some of these distributions that we should have up our sleeves on Thursday. But if you have any questions, let me know. Otherwise, I'll see you then. I'll go. Oh. Yes, I'm just going to stop this recording.